All right. I will begin with the word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to be with us today. Help us to just learn a little bit more about calculus and just to answer any questions that remain. And just to pray that we would glorify you in what we do this morning. Lord, in your name I pray, Lord Jesus. Amen. Lest I forget, here's the attendance sheet. So, let's see here. I'll start with your question. Last time was about iteration. So like iterative formulas. Is that the question?
Recursive formulas?
Recursive formulas, yeah. Like, so there are recursive formulas for like most of your favorite basic elementary functions, because typically what happens for an elementary function is like the integral or the derivative somehow loops back where it starts. And whenever you have that kind of pattern, integration by parts tends to cycle back to where it starts and then give you some kind of like formula that relates the nth to the n plus 1th, you know. So here we can try one. For example, we can look at like the integral of cosh to the n, you know, of x dx, and we can see if we can discover an iterative formula for this. I think we probably can. Let's see how it goes, yeah? So to get started, I'll let this be u, I'll let this be dv, right? And that's going to give me x cosh n of x minus the integral of what? So notice here that u, I'm going to rewrite that in a slightly different notation. That means cosh of x to the n power, right? So the derivative of that is n cosh n minus 1 of x sinh of x dx. All right. This is a waste. This needs to be fixed. Maybe this weekend. I need to take some measurements. I can fix it. Some of you guys are in my physics, right? Yeah. Those are my boards. I mean, I'm sorry, some vandal came in over break and put them up without permission, I'm told, but let's see here. Anyway. Well, you notice there's like 2 extra boards in physics? Yeah, those you can put them up too. All it takes is $20 for a 4-foot by 8-foot sheet from Home Depot and about $15 in removable, well, for Sam's, I think Sam's Club is like a $16, like 28 pack of these removable 3M tape hanger things. You put about 15 of those up, it'll hold it. Something like that. It's kind of like Calvin and Hobbes, right? I mean, you just keep driving the trucks over the bridge until it breaks, and then you know the weight limit. I mean, I don't know. I just stick them on there and it sticks. And all right, I digress. Well, V is easier, right? Yep. All right. So what we're up against then is n x cosh n minus 1 of x sinh of x dx, I believe. Right? And then, let's see here, what do we do next? What did I do next? Well, what I did was I peeled off, Oh, rats. I chose poorly. Well, I don't know. I mean, well, I'm not sure this is going to work. I mean, we can keep going down this path. One more step. If we get there, we get there. If we don't, I'm going to bail and go back and do what I did before. Last time I did it, I just tried something, and I started a different way, and I got to the iteration formula pretty fast. I'm not sure what's going to happen here. I mean, I suppose, see, again, I'm going to try this. I don't know if it's going to be helpful or not, guys, okay? I'm going to make this dv2, and I'll make this u2. So like u2 is nx, that makes du2, n dx, and what's my v2 equal to then? Well, v2 should be like the integral, right, of cosh n minus 1 of x sinh of x dx, which we can do, right? This is a integral of w to the n minus 1 dw, where w is equal to hyperbolic cosine. So that is 1 over n minus 1, excuse me, plus 1, right? So 1 over n, w to the n, plus, well, we don't add theta constant, as we discussed at the start of all this. But let me just go ahead and put the integral over here. So I've got x hyperbolic cosine to the n power of x minus big parentheses uv, to u2v2, which is apparently nx over n w to the n. What was w? It was hyperbolic cosine, right? So n over x cosh to the n power of x minus the integral of u2, v2 du2, which in this case is what? Well, you got 1 over n cosh n of x. What? It was my du n dx, yeah? What do you know? Huh. Weird. So I got x. Well, let me let me not celebrate so soon here. Cosh n of x minus x cosh n of x. Oh, that's not a good sign. And I was celebrating prematurely. I thought, oh, it's a minus. What did I forget? The other minus plus integral So what do you do when something like this happens?
I found the answer.
You pat yourself on the back for not doing your homework the day before it's due, and you realize I still have time to fix this, right? So we tried. Let's try something else. Now this could have all been avoided by me looking at my notes, but oh well. So example 1, again. So we you know what, we've had that happen to us before. So if we were a little bit more conscientious about our past, we'd remembered that when I tried that same kind of trick on like secant, that also happened. And when I tried that same kind of trick on secant cubed, that also happened. I mean, we've had this happen to us before, this going nowhere. And so here's what I did in the notes, which will work. We just split off. You just split off a cosh. And by doing that, it will make it go rather differently. So I'm just saying cosh to the n is cosh n minus 1 times cosh, right? We agree? So that's just algebra. Now, I can make this my dv and make this my u. And so we'll have, you know, sinh of x cosh n minus 1 of x minus the integral of n minus 1 cosh n minus 2 of x sinh of x. So this right here is all my du, and then my v is sinh x. All right. Let's clean that up a little bit. This gives me a sinh squared, right? What's sinh squared in terms of cosh? 1 minus cosh squared. Let me see if I believe that. Oh yeah, I don't believe that. Because if I solve that for, that gives me cosh squared plus sinh squared is 1. That is not the truth. How about cosh squared minus 1? Then if I solve that, I get cosh squared minus sinh squared equals to 1, which is the right identity, yeah? So sinh squared is cosh squared minus 1. So I can trade this here is sinh squared, right? So I can trade that out for cosh squared minus 1. What do I get? Well, I'll put this minus n minus 1 out here. And we have integral of cosh n minus 2 of x times parentheses cosh squared x minus 1. I probably should have done a little more algebra there rather than all this writing. Let's see here. So that gives me sinh x cosh to the n minus 1 power of x minus n minus 1 times the integral of cosh to the n power of x dx again, right? Then what? Plus n minus 1 integral of cosh to the n minus 2 power of x dx. Now this is a nice equation. This we can work with. All right, let me try to explain why. So we started with the integral of cosh to the n, right? And what do we have now? See, this is let's say that this is I. Ah, hideous. Well, this is also I, right? Times what? Times this n minus 1, right? With a minus. Now this over here, I'm just going to leave. I'm just leave it there, all right? So what I'm going to do to this equation is I'm going to add, this is n minus 1, put it all the way over here. So if I just, add this to both sides, right? If I add that to both sides, what do I get?
I plus n minus 1 times I.
I plus n minus 1 times I equals to, sinh x cosh n minus 1 of x plus n minus 1 parentheses integral of the cosh of n minus 2 of x dx. Now why is that good?
Factor of that n minus 1.
Yeah, what does this simplify this to? This simplifies, see the...
I times 1 plus n minus 1.
Yes, but how does this simplify?
Just I plus
You get I plus in minus I, right? I minus I, 0, so you get ni here. So divide the equation by n, and we have it. The integral of cosh to the n of x dx is equal to 1 over n. Sinh of x cosh to the n minus 1 of x plus n minus 1 over n, parentheses, integral of cosh to the n minus 2 of x dx. And this is an example of a recursive formula in the sense that it links the integral of the nth power of cosh with the integral of the n minus 2th power of cosh, which is kind of nice because it gives you a way to generate a bunch of integrals of hyperbolic cosine just by getting one. You can kind of just build your way to the next. I don't expect you to really memorize these, yeah, but you should be able to derive it if you were asked. Now, I typically say, if a problem like this on a test, I would typically ask it in the form of, show this is true. That would be the typical format of that question, which is also true for Stewart. If you look at the homework problems he has, he's like, show this is an iterative formula for secant or whatever. I think to keep score in here, we've derived the iterative formula for sine, for secant, and now for hyperbolic cosine. There are iterative formulas, I think, for tangent, for cosine, for, I think there's even one for like 1 over an irreducible quadratic to a power. Although I don't know if I know that. I'm afraid to try that right off the top of my head. Does that answer your question? I mean, we can put this into practice to calculate the integral of like cosh cubed if you want.
No, it makes sense. it made it easier once you did cosh n minus 1, so you can split it up.
Yeah, yeah,
That makes sense.
yeah. So, I mean, as you saw today, you might not start in the right path if you try to derive one of these, but you just kind of have to tinker until you see something. Other questions? Yes, sir.
On the practice problems,
I can try.
I guess
Annoyingly, I have left my phone up in the office, which I took pictures of the book on, and so you'll have to tell me the problem. Yeah.
It's the integral of the square root of x squared minus 1 over x to the 4th.
Okay, the integral of the square root of x minus 1.
X squared minus 1.
Oh, x squared minus 1 over x to the 4th?
Yep.
All right. So, well, there are two paths to go down here, right? And I could either try, although I should mention something, guys, before I forget. Before I forget, something I have neglected to mention is something like this, right? So, like, if I had 2x dx over the square root of x squared plus 1, right? You might be tempted to do like an x equals sinh substitution there, given our recent conversation, right? But that would be dumb. Because we should always remember, if we can make a u substitution, by golly, it's easier, right? So that has really nothing to do with your current question, necessarily. But, you know, this integral is as simple as this, right? Because this integral is actually calculus 1, which you may or may not know. But because some of you took calculus 1, and others of you took calculus 1 a while ago, and others of you took calculus 1 more recently, but, well, I won't say anymore. Let's see here. You know what you did. Let's see here. So straight line. But let's see here. So anyway, integral. Sorry, I'm misbehaving. But what should we do?
I tried the trig substitution, but it like came out with a weird trigonometry integral, and I was like, I don't like that. So.
You tried a trig? I mean, I can try your trig substitution. What did you do?
I tried. Let's see here. I did secant x equals secant x.
That sounds right. Because then x squared minus 1 would be secant squared theta. I mean, x. Oh, good grief. Look at this. Oh, my goodness. Take away 50 decipoints from my quiz right now. This is totally wrong. You cannot make a substitution using the variable you already have. That is the one letter you cannot use. Theta is what I usually do there. So, OK. Secant squared theta minus 1. I mean, we're substituting a theta integration for an x integration, right? We can't put x as the angle. And maybe 10 people in here did that on the quiz. So you're not alone if you did that. But don't do that. You got to get that out of your system. I mean, it's a time-honored mistake. It's in every Calculus 2 class, so like there's that. It's a proud history of that mistake. But, you know, on the quiz is fine. Quizzes are worth, you know, relatively little. You know, so hopefully the quiz helped you see, oh, I shouldn't do that. That's the point, right, of the quiz. And now secant squared theta minus 1, I think, is tangent squared theta, right? So let's see here. So we've got the square root of tangent squared theta, which is tangent theta. And then x to the 4th is secant to the 4th. And then my dx would be secant theta tangent theta, d theta, which, let's see here, what are we up against? We're up against tangent squared theta divided by secant to the 4th theta. Oh yeah, I was leaving that other secant out. I mean, I don't disagree with you guys. I just wanted to look at like that for a second. Actually, I don't really want to look at it like that. I want to, oh yeah, yeah. Huh. Are you guys seeing something? Okay. I mean, either for the simplest thing, I'm looking either to like separate out a secant theta, tangent theta, d theta, right? Or like a secant squared theta, d theta. Those are the two kind of things I'm trying to see what that looks like here. So let's just do that. So if I separate out a secant tangent, I've got what? I got a tangent theta, over secant to the fourth theta, secant theta, tangent theta, which is not terribly nice. And then if I look at the integral, if I pull out a secant squared theta, I got a what? Tangent squared theta over secant to the fifth theta, secant squared theta d theta. And so like this would be, I'm thinking about like a u equals, secant substitution. Here I'm thinking about a u equals tangent substitution. And you see, though, neither of those are nice here because, why? Like here, you've got the tangent left over upstairs, and converting tangent to secant is not nice, right? And same story down here, right? Like, yeah, I can convert tangent squareds to secant squareds or vice versa, but I still got a leftover secant. So I don't think either of the elementary u substitutions looks nice here. So what do I do then? Yep.
What if we turn tangent squared theta into sine squared theta over cosine squared theta, and we turn secant theta, 1 over secant theta into cosine theta?
Very, very good. Yes, you read my mind. So you're like, convert to, let's try sine and cosine instead, since secant and tangent's going nowhere.
Yeah.
Right. That's a good, that would be my next. Perfect. That would be the next move here. So how's that simplify? Well, here, let me just one more step here. So that's tangent squared. I'll do what you guys told me to do back, 5 minutes ago. Secant cubed theta, right? That's everything put together nice, right? Now let me just convert to sine and cosine from there. Like you said, tangent sine over cosine. And secant's what? 1 over cosine theta, right? So this is actually the integral of sine squared theta over cosine squared theta for my tangent theta times cosine cubed theta d theta. At which point I go, oh, well, this is not an unfriendly problem. Actually, this problem I think is easy. Sine squared theta. I got to be careful here. If I get too prideful, you know what'll happen. So sine squared theta. That was your idea. So anyway, oh, now we can make a u equals sine substitution, right? Hey, check this out. Here's the Asian notation for this. You don't even have to write down u. It's the differential of sine theta. You're integrating with respect to it the answer. 1/3 sine cubed theta plus a constant, right? This is a way to do u substitution without writing the u.
What way is that?
You will find this in no American textbook, but it's commonplace in Asian calculus courses. Yeah.
Why did that function?
Going from here? You asking?
Oh, I know, never mind.
So I'm using something that you may have forgotten. So the differential of a function, right, is like f prime times, well, in this case, f prime of theta d theta, because f is a function of theta.
No, yeah, I meant at the last 2 lines, but then I wrote those down.
Oh, okay. Oh, and then we should make it pretty, right? So what's the substitution here? The triangle. This one's not curvy. It's a. Man, I'm glad you guys talked me back into. Let's see, I'm glad you guys talked me back into the sine and cosine, because I was about to try a hyperbolic on this, and that would have been silly. So I think that's 1 over cosine, which is hypotenuse over adjacent. Yeah. So if you use your imagination, you see there's a 1 down here. So 1x, and that puts the square root of x squared minus 1 over here. So that makes my sine cubed 1/3 square root of x squared minus 1 to the power 3 plus a constant. There you go. And I can totally see why you got hung up on this problem. Like, it's got some dark alleys to get stuck in, I think, yeah.
Yeah, I guess I know all of them.
And what? And all of them? No, I don't believe that. Other questions? Yeah.
This one on the homework, it's like, it's the integral of dx over the square root of x squared.
Which number is it?
28.
Ah, come on. So it's kind of like the one I just dismissed. Why? I mean, we conquered it quickly with what? With a u substitution, right? But this one asks, yeah.
Isn't it the
What
square
have I
root
done?
of square minus 1 over x sine is opposite over hypotenuse?
Oh, yeah. Sorry, I've seized defeat from the jaws of victory. There you go. Thank you. Yeah, I always be leery of my last step. It's where I usually make my mistake, honestly. Okay, so let me come up with one that is similar to the problem in the homework, but not the same. Let's see here. Well, can I erase all this now that we've clarified it? You guys good?
Yeah.
Cool. Now I would take the bait from Dr. Sprano yesterday and work that problem, but like I told you guys, I left my phone in my office, so unless one of you has written down the dastardly problem that Dr. Sprano left on the board, I've forgotten it. So it's in my phone. I'll bring it back Monday if nothing else happens. All right, so here we go. Let me make it slightly uglier than the one in your homework. All right, so suppose you've got, oh, I don't know, 3x squared plus 20x plus, I don't know, 900. There. It's kind of ugly. How do you integrate this thing? And I further cramped your style by insisting on a hyperbolic substitution. All right, integrate by a hyperbolic substitution. How's that going to go? Well, the first order of business here is to clean up that quadratic, right? So what do you want to do? What's that? Complete the square. Yeah, but before we even do that, I guess it depends on what you mean by complete the square, but yeah, I agree with your general sentiment, but let's factor out a 3, right? So that's 20 over 3 and 300. Are we good? I hope. Now we can complete the square. What's half of 20/3? We have x plus 10/3, yeah? Quantity squared. And then I have to subtract 100 over 9. And I'm going to add that to 2700 over 9, I think. And I've lost my square root. It's not a good sign. Let's get it back. There we go. It's not too late. Okay, so clean that up a bit. What are we up against here? 1 over the square root of 3, integral of dx over square root of x plus 10/3 quantity squared. Looks like 2600 over 9, so This is definitely like a prime polynomial, right? Or an irreducible one. If you were to graph the thing inside the square root, it would never cross the x-axis, right? It's an irreducible. Its discriminant's negative, if you know about that. You ought to know about that. Anyway, so what does this suggest? So hyperbolic-wise, remember, I remember this, cosh squared phi minus sinh squared phi is equal to 1, which tells me cosh squared phi is equal to 1 plus sinh squared phi. So that suggests that we make a hyperbolic sign substitution here. So what I'm going to do for this one is I'm going to put x plus 10/3 equal to, the square root of 2600 over 9, which of course you could simplify, right? But anyway, that's just what I want. Square root of 2600 over 9 sinh theta. Sinh phi, rather. And you could use theta here. I just use phi for the hyperbolic ones, just to be different. It's a show of respect for rapidity in special relativity. We use the symbol phi for what's called it's called rapidity in special relativity. But anyway, so with that substitution, what happens? X plus 10/3 squared gives you what? Well, x plus 10/3 squared plus 2600 over 9, right, gives us 2600 over 9 times sinh squared phi plus 1. So with this substitution, we get our dx, of course, is square root of 2600. Good gracious. 2600. Why did I make it so ugly? Oh, it's because I'm always accused of sometimes as math professors we're accused of working, pretty problems in class, but putting ugly problems in the homework. I like to flip the tables on that sometimes. So cosh phi, but maybe that's bad pedagogy. Maybe I should only work simple problems in class. I don't know. Maybe I should just talk less. Cosh phi d phi times that. That's the differential, right? That's dx. And then we're taking the square root of the, this guy here, right? So what happens there is you've got, square root of 2600 over 9, yeah? And this is what? Cosh squared phi, right? So this is cosh phi. So, yeah. This is just 1 over root 3 integral d phi. Yeah.
For x plus 10 over 3 on the right, when you're doing the substitution, equals square root of 2600 over 9 sinh phi, or sinh phi. Is that supposed to be code?
This here?
No, up one. Is that supposed to be code?
Oh no, I set x plus 10 over 3 equal to square root of 2600 over 9 sinh phi. So I'm just plugging this into here, and I square it, I get that. But then the plus 1 is this piece here. I factored the 26. I'm not sure I'm answering the same question as you.
Well, I am trying to figure out what you did at the end. What?
Here?
Yes. How did you get?
Well, sinh squared plus 1 is cosh squared phi. So this is literally the square root of 2600 over 9 cosh squared phi.
You got the plus 1 by factoring out taking out the 2600 on top.
Right, I factored that constant out. So the first piece under the square root is literally 2600 over 9 sinh squared phi, right? So I've got a 2600 over 9 on both of them. I factor it out. It gives me sinh squared plus 1. Yeah. Yeah. Don't worry, nothing, you're not missing much here. So this is 1 over the square root of 3, phi plus a constant, which is 1 over the square root of 3. Now I got to solve for phi. What is phi equal to? This gives me phi is equal to inverse hyperbolic sine of x plus 10 over 3 divided by that ugly constant, yeah? 2600 over 9. Which of course you could simplify a bit, right? What is 2600 over, what's the square root of 2600 over 9, by the way? It's the square root of 2600 over 3. So what I'm really looking at there is inverse hyperbolic sine of, well, 3x plus 10 divided by the square root of 2600, I think. Let me double check on that. So this is, I get a 1 over 3 in the denominator, so that flips up and multiplies by 3. When I multiply by 3, I get 3x, and 10/3 times 3 is just 10. So I think that's right. Now, if you had a particularly draconian Calculus 1 instructor, this could have been a basic integral for you. Why? How about this? What's the derivative with respect to theta of inverse hyperbolic sinh of theta? Let me make it an x to make it more friendly. Maybe not x. Let's go with, oh, fine, x. So we do what? I put y equals inverse hyperbolic sine of x. I take the sinh of both sides. I'm deriving the derivative right now. I differentiate both sides. I get cosh of y times dy dx is equal to 1. That gives me dy dx is equal to 1 over cosh y, right? Which is, by the way, 1 over the square root of 1 plus sinh squared y, also known as 1 over the square root of 1 plus x squared. There you go. The derivative with respect to x of inverse hyperbolic sine of x is equal to 1 over the square root of x squared plus 1. Which then means, of course, the integral of like du over the square root of u squared plus 1, well, this is an elementary integral. In perhaps a somewhat ridiculous abuse of the word elementary, but there it is. So if you understand that, you just complete the square in this and make a u substitution. See, because our original integral, you can repackage what I have over the square root of, what was it, 3x squared plus 20x plus, what was it, 100? 900? So by the algebra we just did, that's dx over, square root of 3 times the square root of x plus 10 over 3 squared plus, oh rats, I got a little bit more algebra to do. 300 was it? 100? What I got here? 300. All right, so I need a little bit more pre-processing here. Divide the 300 out, what do you got? See, I can do square root of 3 times 300, square root of 1 plus 1 over 300, x plus 10 over 3 squared. I could do that. I can make that 300 become a 1. And then I can put all my variableness into the squared term there. And then I basically just say, well, I'm going to make this a u squared. So I make my u, x plus 10 over 3 divided by the square root of 300, if I haven't made a mistake here. And in doing that, my dx becomes square root of 300 times du. And I'm left with, square root of 300 du. Oh, sorry. Square root of 3 times 300, square root of, 1 plus u squared. The 300s cancel, and you're left with, 1 over the square root of 3 du over the square root of 1 plus u squared, which is 1 over the square root of 3 inverse hyperbolic sine of u. But what was u? X plus 10 over 3, right? Divided by the square root of 300. And then, of course, you're left with the question, why are these the same answer? Feels wrong. I guess if I multiply the top and the bottom, let me do the math over here, up here. Everybody can see it. So I've got x plus 10/3 over the square root of 300, right? If I multiply this by 3 over 3, we agree that's equal, right? So that gives us 3x plus 10 divided by the square root of what? What happens when you bring the 3 inside? 9 times 300. So how did I get? Oh man. I must have did this wrong, yeah?
Yeah. When you complete the square, it's not 300. It's 27 over 9 minus 100 over 9.
Oh. All right, well, I'm not going to all do that over again. You guys get the spirit of it anyway?
Yeah.
My point is, if you're willing to do the algebra, you can make this a u substitution if you know that inverse hyperbolic tangent is available for integral. Inverse sinh is the integral of 1 over the square root of 1 plus x squared, right? If you know that, then this becomes a u substitution. But I think it's easier as a hyperbolic substitution. And your homework problem is easier than this, right? Because your homework problem doesn't have a stupid 3 in front of the x squared, which results in fractions. And yeah. So just to be clear, we made a mistake. So I know everybody's going to keep, I'm going to be asked about this about every minute for the next 5 minutes. So the mistake was right here, right? I think. Isn't that right? Okay. So wrong. And then everything that follows from it, well, it's correct in the spirit of the calculation, is not arithmetically on point. Yeah.
So where do we find all of the hyperbolic trig substitutions?
Oh, my notes. They're all in my notes.
Is it in your website? Or?
The PDFs that I wrote for you guys, what I said is, essentially serves as the textbook for you. So I have, it's in the integration techniques it's right at the end of the implicit substitution section.
Is it in Canvas or like the links?
It's in,
You can find it through so he did make an announcement like first week. If you go into announcements, you can actually, it'll tell you the link to the website. Through the website, you can find it.
So if we go to my website, that's probably the easiest thing is I probably put it in Canvas, but I would rather that you know where it is on my website, because then you know where it is when Canvas breaks.
Yes, sir.
And so listen, my website is supermath.info, and this come on. Well, you can do it. You can do it.
ridiculously.
You can do it. Do it. All right. So guys, for those of you who don't know, my course website here, Calculus 2, right here. And then, so you see here, I have, these are the articles from which I teach. At the moment, we are on integration techniques and improper integration. In this integration techniques, there's everything I've taught you and I think more. So, and then, you know, here I'll look at it. I don't like to look at it in the web browser. Like, it's better to look at it in Adobe. If you go to implicit substitutions, at the start of this section, I have the, you know, the triangles for when. Now, admittedly, we have modified that a bit for examples, right? Because we complete the square. But then at the very end of this, oh, come on. Well, I guess I'll have to scroll. But down here, eventually, at the end of that, I have those triangles we looked at before. This is the hyperbolic substitutions is back here. So, 3. So, yeah, they're all in the notes. And by the way, I don't think we've done enough definite integration in here yet. I still owe you an example or two of that. So maybe we'll actually show the area of the circles pi r squared next week. How about that? Have a good weekend, you guys. So.
I would say it, but I'm going to see you in a few days.
Oh yeah, that's right.
Just let you know, I do the
Still got the physics. Turn this thing off before I forget.